Hi, welcome back to my YouTube channel. Today I want to finish the last video on non-abelian Yang-Mills gauge fields. So we're going to do lesson 3.5, video 4, the geometry. Geometry of gauge fields. And so I'd like to start by reviewing some previous equations. And this video will be more of an outline sketch than I usually do. And so most of these equations were in the previous video, and we worked on a U1 non-abelian field, and we had things like del phi equal minus I lambda phi, d mu phi equal to the partial of mu phi minus I e a mu phi, and then del d mu phi is equal to minus I lambda d mu phi. This shows that d mu phi transforms covariantly. And then we had our gauge field. How did that work? And it was just 1 over e, the partial of mu lambda. Then we had our field defined as f mu nu equal to the partial of mu a nu minus the partial nu a mu. So this is all like basically electromagnetism. When we went to our SO3 non-abelian field, the equations were more interesting. And we had like and remember, vectors always indicates internal indices, not space-time indices. We had a vector field, and it would transform that way. And then we found we could get a covariant derivative that worked well, but we had to introduce another potential field, which is a vector now, whereas before it was a scalar like a mu. A mu is a space-time vector, but it's a scalar with respect to like the internal group. Then again, this is how we want things to transform covariantly. I'm going to leave out a lot of these vectors. And then we had how our potential transformed. This doesn't transform like covariantly because it's a gauge thing. There's an inhomogeneous term, sort of just like in electromagnetism. And then we defined our field. This is like f mu nu, but here in this case it's a vector, not a scalar. But the field itself transforms exactly like we want it. And I also had one last equation that when we take a covariant derivative of the field, we don't lose. It's still a nicely covariant object. Okay. So what we want to try and do is reproduce these results and generalize them to a geometric framework. So we can write phi goes to phi minus lambda cross phi, we can write this as phi goes to phi prime, which is equal to e to these matrices I. This is a set of 3 by 3 matrices. And we're going to apply this transformation. And the i's are the representation of the SO3 group. And I'll even write them down explicitly. You've probably seen these before. It's I1, I2, and then I3. So these are what are known, the i's are what are known as the generators of the group. And the general formula for at least this SO3 group so infinitesimally we can show this as just phi prime m is equal to 1 plus I lambda I mn phi n, which is equal to del mn plus epsilon I mn lambda I times phi n. Now this is equal to phi m minus epsilon min lambda I phi n, which is equal to phi minus lambda cross phi m. That was the same formula we had above when we started over here. So so it works. So this is the adjoint representation of the Lie group, Lie algebra, or I'm not going to distinguish between the Lie algebra and the Lie group. In general, if you have like, for instance, if we're dealing with a group like SUN, if memory serves me correctly, I think it does, this has n squared minus 1 generators. In other words, this is an n squared minus 1 parameter group. So you can see with SU2, which is isomorphic to SO3, we have 2 squared minus 1 equal 3 parameters. If we were to do like QCD, SU3 would have 3 squared minus 1 equal 8 parameters. And you notice that we also have 8 gluons. So with respect to, in the adjoint representation, with respect to each parameter, we get a gluon. Okay. Now, so in general, when we let the parameter depend on space-time, as we did previously, you know, we go phi goes to phi prime equals the exponential of I. I is the, these are the matrix representations, but now we have a space-time dependence. And we're going to say, in general, we're going to get some matrix times phi. And in the case of the SU2 or SO3, this would be a 3 times 3 matrix. Now, if we were dealing with spinors, so like SU2, we would have like psi goes to psi prime equals EXP. And now we would write the generators, and this is sort of a matter of convention. Tau is the Pauli matrices for internal space. And we'd write this as SX psi. This would be a 2 times 2 matrix. So in general, with an n-component object, we'll call it the same thing. We have the index A goes from 1 to n squared minus 1, for example, for SUN. And we have things like psi x goes to psi prime x is equal to EXP. And now we're going to write just in general I, MA. These are the generators of the group Lie algebra. Lambda A is the parameters which depend upon x, which is space-time index, psi of x. And we're going to write this, always call this S of x, psi of x. And this, in this case, this would be an n times n matrix. And if we were to try and form a covariant derivative, we would notice that when we take the derivative of partial mu of psi prime, we get S partial mu psi. This is the part we want. But we also get the partial of mu S times psi. This is the... so it doesn't transform covariantly. It would transform covariantly if we just had this term. Good. This term is bad. So this is not a covariant derivative by itself. And so what we do, we found the solution last time algebraically. We worked out what d mu psi needs to be, at least in some situation, algebraically. But now we want to take a more geometric approach. So what's happening here is that we have internal spaces like this. Let's call this internal space. But at different points in space-time, let's say this is at x, internal space at x in space-time. At another point, x prime, the axes could be rotated. So in order to compare, to form a covariant derivative, we have to take into account this rotation. And in general, you can write it as del psi is equal to I, G, MA. These are the generators of the group. A mu A is a new field we're going to introduce. Mu is the space-time part of it, and A is the in the representation. Previously we were doing the vector representation, but it could be a spinor representation or an SU3 representation. It's usually also proportional to the amount of space-time that you've difference between the 2 points, and it's proportional to psi itself as well. So this AA mu, Feynman called influence potential. Tells us how much the axes are rotating. So what we do now is we define the covariant derivative as d psi is equal to psi plus d psi. But we have to take into account how much they've rotated. And so we get psi plus del psi. This is equal to d psi minus del psi. And for those of you who have taken general relativity or studied some differential geometry, this is the same thing we do with covariant derivatives when we're using regular coordinates. So we have our expression is d psi dx mu, which is defined to be d mu psi. Covariant derivative is the partial of mu psi minus ig ma aa mu psi. Very important equation. Call that a box. Now, let's just check against like our previous results. For example, for U1, where we had our transformation when phi goes to e to the minus I lambda phi, and we compare that with psi goes to e to the I ma lambda a psi. So what we see is the only difference is a sign, and here we're working in one dimension, so this implies, at least for U1, m is just equal to minus 1. And we can replace g by e if we're dealing with like electromagnetism. So now we get that d mu is equal to the partial of mu plus I e a mu. And that's what we wanted. Notice there's no internal index because we're just dealing with a one-dimensional thing. Now let's do SU2. Maybe it's really SO3, the same group. So we have MA, MN, as we showed earlier, is equal to minus I epsilon AMN. So here we would get d mu phi m is equal to the partial of mu phi m minus IG MA MN a mu a and phi n. We're just multiplying the representatives times the field. Now this is equal to the partial of mu phi m minus, remember the definition here, so I get minus g epsilon a m n a mu phi n. This is equal to the partial of mu phi, if I write it just in vector notation, plus g, say we write this as the m component, plus g a mu cross phi, and we take the m component, or what's the same thing, d mu phi is equal to the partial of mu phi plus g a mu cross phi. So this is the same thing we got before in the last lecture. In the last lecture we called W mu instead of, and now for A mu. Okay. Now for a spinner, let's do the case of a spinner, covariant derivative. M is now defined as tau over 2, and d mu psi is equal to the partial of mu psi minus I over 2 tau dot A mu psi. And we sort of left the G. Sometimes we incorporate the G in the potential, so I think that's what I did there. Now, the analogy with differential geometry in differential geometry we have d nu of a vector field is equal, this is the covariant derivative. Indices up and down matter here, but so these things are called the connection coefficients. And they're defined, or at least in standard general relativity. Let's see if I remember this. I might be off by a sign here. A comma means a derivative. Okay, doesn't really matter, but that would be in terms of the metric tensor. G is so in general, we have, as we said before, psi goes to S psi, and d mu psi goes to d prime mu psi prime is equal to S d mu psi. And we also define our vector A mu is equal to M A mu A. This is a matrix over here. This is going to be, M is the representation matrices, A mu are the fields, and then when we sum, we're just going to get a matrix here. Okay, and so we previously, I'll just write it down again, it's equal to the partial of mu psi minus IG MA AA mu psi. Now we write it just as the partial of mu minus IG A mu psi. It's important to realize that that when I just write A with a single index, it's actually a matrix. So if we use this over here, we can derive, I'll do it very quickly, the partial of mu minus IG A prime mu psi prime. That's what this is equal to. This is equal to S partial mu minus IG A mu psi. Now, so all of this is in Ryder section 3.6. He leaves out a few things. I'll just show you. So I would get the partial of mu Now I have psi prime is s psi, using psi prime equal s psi. So when I take the derivative, I'm going to get the partial mu s times psi plus s the partial mu psi. And I'm going to get minus ig a prime mu s psi. And this is equal to s the partial mu psi minus ig s a mu psi. So this term cancels right off the bat. And we're left with all these things on psi. We can sort of cancel that. Understood that everything will be acting on psi. So let's get rid of that. And now we can just rearrange the terms and divide by minus ig. First multiply by s inverse on the right. So I get the partial mu s inverse. And then s inverse is the identity, so that cancels that. So I get minus ig a prime u. This is equal to minus ig s a mu s inverse. And now it's so we move this to this side, move this to this side, divide by minus ig, and you get a prime u is equal to s a mu s inverse minus I over g the partial mu s inverse. And again, this is the way our usual thing would transform. And this is the inhomogeneous part. Which we have for a gauge field. Gauge potential. Okay, so let me box that. Now let's just see how it works again. For U1, we have S is equal to e to the minus I lambda. Partial mu S is equal to minus I, the partial mu lambda, e to the minus I lambda. We're going to make the substitution. G goes to E and M goes to minus 1. And we'll end up with A prime U equals A mu. See, if you just do the substitution directly, you'll get a minus I and then a minus I, and you'll get a minus sign. And you say it's supposed to be a plus. But then we change the A's because they're the matrices, but M is minus 1. So each of these, in the first two terms, the one on the extreme left and the first one on the right, they get negative signs. So everything ends up being plus. We get A prime A mu plus 1 over E, the partial of mu of lambda. So that's good. That's what we had previously. And then let's try the same thing for SU2. Now here we're going to verify in the infinitesimal case. So we have S is equal to e to the I over 2 tau dot lambda, which is equal to 1 plus I over 2 tau dot lambda. And again, our definition of A mu, I'm going to put a vector on top of A mu, or, well, I'll leave the vector off, but A mu is equal to tau over 2 dot A, let me go back here. See, this is this is our definition of a mu. It has the representation times the fields. And so this is the representation, tau over 2. And I'll just put a mu because it's going to be the same indices. So now we have, once again, a prime u equal to s a mu s inverse minus I over g partial mu s s inverse. So this is going to be 1 plus I over 2 tau dot lambda. You know what? So, yeah, okay, so that's the definition of A, but I'm actually using tau dot lambda. A mu 1 minus I over 2 tau dot lambda minus I over g I over 2 tau dot partial mu lambda s inverse. Okay, because when I take the partial mu s, not sure if I did that here. Yeah, it already has an s inverse. Okay. Well, the partial of mu s is going to just give me a an s with the I tau dot the partial mu lambda. It's just the chain rule. So this is basically equal to a mu plus I over 2 tau dot lambda a mu minus I over 2 tau dot lambda, sorry, a mu tau dot lambda plus 1 over g tau over 2 partial mu lambda. Now this is going to be equal to, I'll just to clarify everything, I'll put these things. So this is like tau I over 2 ai mu plus I over 2. And now I'm going to do like tau dot lambda. Then a mu is it's also tau dot the vector a minus tau dot a tau dot lambda plus 1 over g tau over 2 dot the partial mu lambda. Now this is going to be equal to I'm going to get a you know what, I left there's like a 2 over here as well, 2 over there as well, so I get I over 4. Now we use the basic identity of the Pauli things, you know, tau dot a, you know, I want to use different letters. Let's do it over here. Yeah. Tau dot x, tau dot y is equal to x dot y plus I tau dot x cross y. This is the vector cross product. So I have I over 4 lambda dot a mu plus I tau dot lambda dot a mu. So I lambda cross minus a mu dot lambda. These two cancel over here because for for dot products, the order doesn't matter. Minus I tau dot a mu cross lambda plus 1 over g tau I over 2 partial mu lambda I. Going back and forth between vector notation and everything, but so we're going to end up getting, this is the equation that I want, a prime mu is equal to a mu minus lambda cross a mu plus 1 over g partial mu lambda. And if you remember back on our previous lecture, this is exactly the same, except previous lecture, instead of A, we had W. Okay. Now, just to show some of the relationship to general relativity, and differential geometry, the same techniques are sort of used. In general relativity, we define the Riemann tensor and one way to define it is to take a vector in space-time and transport it around, let's say a square, let's say this is V, then we move it over here and it's like rotated a little bit, then we move it over here and maybe it's rotated a little more, then over here it's rotated a little less, and then finally it comes back to here. And what we find is that the amount that it's rotated to, we can write it as proportional with a tensor of the area element. And this defines our Riemann tensor, which for those who have seen general relativity, and you can see how these formulas, except for the fact that there's a few more indices, are basically the same as what we're developing in our gauge theory here. I think this is a row. This is a row. So this is our Riemann tensor. And we can do the same thing for the gauge fields, gauge potential in internal space. And I won't do the whole calculation for you. It's done in Ryder, pretty good detail. But basically he has that the field, when it's transformed around a loop, 1 is like the new one and 0 is the old one. It ends up being 1 plus it's proportional to the area element in space-time. And then it has this commutator of covariant derivatives, which is very similar to these things over here, times psi a comma 0. So we can evaluate the commutator d mu d nu is equal to using our previous formula. Remember, these things are matrices. This is equal to minus Ig partial mu a nu minus the partial nu a mu minus Ig, the commutator, a mu comma a nu. And so now we can define a gauge field. And we'll define this as G mu nu is equal to the partial mu of a nu minus the partial nu of a mu minus Ig, the commutator, a mu comma a nu. This is what's missing. This is the new term that's missing in electromagnetism, because in abelian the things commute. So anyway, this leads to d mu, the commutator of the covariant derivatives, is equal to minus Ig, the field. Okay, so for U1, the commutator vanishes and we just get our usual field tensor. And for SU2, this is the internal index, the A. Now, if we were working with like SU3 or SUN, the structure coefficients would be different of the group. Different. And so that would change the epsilons, which apply to SU2 and SO3. Anyway, in vector notation, this becomes and it's also not hard to show that that G mu nu transforms covariantly Notice in U1, F not only transforms covariantly, but F is invariant. It's like a scalar. This used to confuse me. So in electromagnetism, our scalar our term in the Lagrangian would be like F mu nu, F mu nu. But when we're doing like QCD or the weak interactions, this isn't a scalar. It's a space-time scalar, but it's not a scalar internally. What we do is we take the trace. So it's a little differently. And of course, in a way, you'd expect that because these are matrices. So when you multiply them, you get a matrix, and then you need a scalar for the Lagrangian, so you have to take the trace. In general relativity, we have, I'm finishing up here, we have the Bianchi identity. I'll just write it down. For gauge theory, it's the same. We call it the same thing. And it's very similar. We have d rho G mu nu plus d mu And we can also write this, oops, we can also write this if we substitute our definitions for G mu nu, comes like this. Which I'm sure many of you have seen before in different ways. This is none other than our old Jacobi identity. So in electromagnetism, because of the way it works, in U1 it's very simple, and we get an equation which you've all seen as well. Which is the homogeneous Maxwell equations. For non-abelian gauge theories, we have this, which is a lot more complicated. So that's all I want to say today. One thing you can see is that it all comes down to the geometry is very similar. The geometry of gauge fields is very similar to the differential geometry that you use in general relativity. There's a few more things, fiber bundles and various other things, but it shows how important geometry is to understand some of this stuff. You can do it algebraically, but it gets kind of hairy for a while. And when you look at the geometric meanings, it's much more interpretable. So that's all I want to say today, and I'll see you next time. Bye-bye.